Welcome to NORA's Gold Certification Series Advanced Venting course. This course will be presented in 4 chapters that correspond to NORA's Advanced Venting Manual, which you need to download at the very beginning of this course. And this course will explain the various venting systems available for oil heat appliances. Chapter 1 will talk about the basics of venting. Chapter 2 will cover chimney venting. Chapter 3 will cover alternative venting systems, which include power venting and direct venting. And Chapter 4 will talk about venting of condensing appliances. Let's start off with Chapter 1, Venting Basics. A properly functioning venting system of an oil-burning appliance removes all of the combustion gases from the appliance and safely directs them to a point outside the building. The proper venting of combustion gases is an extremely important function, one which relies on the performance of the entire venting system. The consequences of malfunctioning venting systems, such as improperly pitched or improperly assembled flue pipes and/or a deteriorating chimney, could lead to property damage, personal injury, and even death. Before examining the various venting options available, it is important to understand the need for adequate air to support combustion, dilution, and ventilation. Air typically enters a building by infiltration, typically through leaks around the foundation, building penetrations, windows, and doors. Combustion air is the air that enters the burner through the air bands and mixes with oil during the combustion process. Combustion air adjustments must be made according to the manufacturer's requirements for safe and efficient operation. Dilution air is the air drawn into the vent system through the draft control or other openings. The draft control adds dilution air to relieve excessive chimney draft and assist in maintaining proper overfire draft, which maximizes the amount of time that the combustion gases transfer into the heat appliance. Ventilation air is the air around an appliance that prevents the area from overheating during appliance operation. This reduces the possibility of fire due to excessive heat and drying of combustible material within the space. All heating systems are designed to operate when the building's thermal envelope is under neutral pressure. In this picture, the burner is taking in combustion air, and the draft regulator is admitting dilution air into the flue. Adequate infiltration air, also known as makeup air, is critical for systems to operate safely and efficiently. Oil burner combustion requires a great deal of air to operate properly. Approximately 1,500 cubic feet of air per gallon under ideal conditions. This does not include excess air required for safe, efficient, and repeatable operation, which means that a minimum of 2,000 to 2,200 cubic feet per gallon is a more reasonable number. As homes continue to get tighter, the amount of air required truly depends on the individual building's leakage rate. For years, it was assumed that heating appliances had adequate air available based on the building's natural leakage rate. Improvements to both new and existing buildings have significantly reduced natural leakage rates. Insulation, tight windows and doors, tight construction can provide outside air from entering the building by infiltration. As a result, buildings cannot breathe and receive fresh air for the inhabitants and for the appliances. The heating system competes with fireplaces, exhaust fans, clothes dryers, and other appliances for air. All of these appliances using the air in a tight house make it difficult for the oil burner to have sufficient combustion, dilution, and ventilation air. In this illustration, the heating appliance, attic fan, bathroom fan, kitchen fan, and clothes dryer are all exhausting air from the house. And for each cubic foot per minute of air that exits the building, there needs to be a cubic foot per minute entering to replace it. If this doesn't happen quickly enough, a pressure differential occurs. In a tight building, the indoor air pressure can drop below the outdoor air pressure, and the appliance can backdraft, allowing products of combustion to be drawn into the building from the appliance and/or the venting system. In this illustration, with all of the appliances operating at the same time, the natural leakage is not sufficient, so air enters the house through the chimneys. It is often said that a service call caused by insufficient combustion air, such as smoke, soot, and/or odors, is the only call a technician can fix just by showing up. As the technician enters the home, the outside door is opened, allowing fresh air to enter. Then, as the basement door and utility room doors are opened, the pressure equalizers and the insufficient air problem is solved. Of course, this is only a temporary improvement, and the situation will reoccur once the doors are closed again. These types of service calls can be difficult to diagnose, and when insufficient combustion is suspected, a worst-case draft test explained later in this course is recommended. Let's spend a few minutes talking about the effects of insufficient combustion air. Insufficient combustion air for heating appliances can lead to property damage, personal injury, or even death. Insufficient air problems are most noticeable on the coldest nights when the heat loss is the greatest and the windows and doors are closed for extended periods of time. These conditions can lead to incomplete combustion and the creation of carbon monoxide inside the combustion chamber and vent system. Carbon monoxide is odorless, colorless, and tasteless. Therefore, in order to detect its presence, technicians should perform combustion tests anytime fuel or combustion air has been dealt with, or anytime the following circumstances are noticed: loose, corroded, or disconnected venting system connections, excessive moisture on the insides of windows or walls, visible smoke in the living space, customer complaints about odors, smoke, headaches, and flu-like symptoms while in the building, a carbon monoxide alarm going off, soot on the unit, burner rumbling, soot streaks around the inspection port, a sooted up CAD cell and/or drawer assembly, or coking at the nozzle or burner head. When performing a combustion analysis, it's important that the appliance manufacturer's guidelines are followed regarding draft, carbon dioxide, oxygen, and stack temperatures. Most of today's oil heat systems operate in the 10 to 12% carbon dioxide range with zero smoke and net stack temperatures of 350 to 450 degrees. In addition, carbon monoxide levels in the flue gas are typically less than 40 parts per million and should always be lower than 100 parts per million. This next section describes confined versus unconfined spaces. When installing new equipment or troubleshooting existing equipment, a determination needs to be made whether the equipment is installed in a confined or unconfined space as defined by NFPA 31. According to NFPA 31, a confined space is defined as a space whose volume is less than 50 cubic feet per 1,000 BTUs per hour of the aggregate input of all appliances installed in that space. So any space that provides less than 50 cubic feet per 1,000 BTUs of total appliance input is considered a confined space. To determine the maximum total firing rate allowable in a room, the total cubic feet must be known. And to determine the total cubic feet of a room, multiply the length times the width times the height, and that equals the total cubic feet. So if a utility room is 24 feet long by 20 feet wide with an 8-foot ceiling as shown in this illustration, you need to multiply 24 by 20 times 8, and that will give you the number of 3,840 cubic feet. To determine the maximum BTU firing rate allowable in this room, we need to start with the volume of the room, which is 3,840 cubic feet. We then need to multiply that times 1,000 BTUs to get a value of 3,840,000. To get the maximum BTU input, and we know that we need 50 cubic feet per 1,000 BTUs, we have to divide the 3,840,000 by 50, and that'll give us a value of 76,800. Which is the maximum BTU input for all appliances in the room. Now let's find the maximum firing rate. Since 1 gallon of oil contains approximately 138,690 BTUs, we can determine the maximum allowable firing rate by dividing 76,800 by the 138,690, and that'll come up with a value of 0.55. So the maximum firing rate for this room is 0.55 gallons per hour. Any unit or units with a higher firing rate requires that additional air be made available. If the appliance or appliances installed in this room have a firing rate greater than 0.55 gallons per hour, this would be considered a confined space. Now there is a shortcut. Since multiplying 3,840 by 1,000 and then dividing by 50 is the same as multiplying 3,840 by 20, you can multiply the room volume by 20 to achieve the maximum BTU input. Chapter 5 of NFPA 31 details the requirements of the standard to ensure that adequate air is available for the safe operation of oil-fired appliances. Section 5.3.1 of the 2020 version reads as follows. In unconfined spaces in buildings of conventional frame, brick, or stone construction, air for combustion and ventilation shall be permitted to be supplied by normal infiltration. It's important to understand that even in unconfined spaces, building improvements made after the appliance has been operating safely for years can negatively impact both safety and appliance performance. NFPA addresses these situations with the following guidance. If normal infiltration is not sufficient because of tight construction, air for combustion and ventilation shall be obtained directly from outdoors or from spaces that freely communicate with outdoors by means of a permanent opening or openings having a total free area of not less than 1 square inch per 5,000 BTUs per hour based on the total input rating of all appliances in the space. NFPA 31 goes on to say that for appliances installed in confined spaces, air for combustion and ventilation shall be provided using one of the methods set forth in Section 5.4. 5.4.1 covers air taken from inside the building. 5.4.2 takes air taken from outside the building. One of the options for adding air from inside or outside is to install 2 permanent openings, one near the top of the space and one near the bottom. For more information, reference the current version of NFPA 31 and the version recognized by the local authority having jurisdiction. As technology changes, NFPA guidelines can also change. One of the significant changes in the 2020 version of NFPA 31 is that it recognizes listed engineered systems that provide outside air and reduces some of the previously required building modifications necessary for confined space installations when these systems are installed. NFPA's worst case draft test, which we mentioned earlier, is explained here. Many people assume that a heating appliance installed in an unconfined space will have sufficient air for combustion, dilution, and ventilation. However, the confined space calculation does not take into account other factors in the home which also affect the amount of combustion, dilution, and ventilation air available. And these may include exhaust fans, range hoods, and microwaves, attic fans, central vacuum systems, fireplaces, clothes dryers. Instead of limiting the amount of air that infiltrates into the home, these appliances remove large amounts from the home. Think about a clothes dryer. When a dryer operates, it causes outside air to infiltrate into the house. Then it heats it and sends it back outside. During that process, a standard dryer blows 1/2 of the air out of a 1,500 square foot home in a single 60-minute cycle. And an Energy Star dryer removes even more air. And that air has to be replaced by infiltration or the pressure in the house will become negative. To address the issues that these devices might cause, NFPA has developed a worst-case draft test that enables technicians to determine if a combustion air problem might arise in the future. NFPA 31 5.2.1 states, after installing a new or replacement oil-burning appliance and before placing the equipment into service, the equipment installer shall perform testing of the worst-case depressurization of the room where the appliance is located and shall determine by measuring the flue draft and overfire draft that the appliance can operate in accordance with the draft requirements of the appliance manufacturer. Essentially, the test simulates what happens if all of the air stealing appliances, except for a whole house fan, are on at the same time. This test was first included in the 2016 edition of NFPA 31, and it, or an equivalent test, is required anytime a new or replacement oil-fired appliance is installed. To conduct a worst-case draft test, the technician should perform the following tasks. First, close fireplace, dampers, and fireplace doors. Then close all exterior doors and windows in the building, and close all interior doors in the building. Step 2. Turn on the building's air exhaust systems at the highest speeds, including the clothes dryers, range hoods, bathroom exhausts, and mechanical ventilation and forced air heating or cooling system blowers. Do not operate the whole house fan. Step 3. Operate the burner in the oil heat appliance with the lowest firing rate first, and then other appliances in order of increased capacity. Measure and record the breech draft, overfire draft, and check for flue gas spillage of each appliance. Step 4. Check that the breech and overfire draft are at a level that is required by the oil heat equipment manufacturer as specified in the installation and operating manuals for the appliance. Overfire draft value in oil appliances are usually negative 0.01 to negative 0.02 inches of water column. Step 5. If the draft is maintained at the manufacturer's recommended level, return doors, windows, exhaust fans, fireplace or dampers, and appliances to their previous conditions of use. Step 6. If the draft is not maintained at the manufacturer's recommended level, take action as needed to correct excess depressurization of the appliance combustion air zone and return the flue draft and overfire draft to the requirements of the oil heat equipment manufacturer. If additional steps are necessary, shut the appliance down until the situation can be corrected. Notify the homeowner, building owner, or occupant if combustion air zone depressurization impacts the operation of the oil heating equipment, and of all actions and modifications that are required to allow the flue draft and overfire draft to be maintained at the level required by the oil heating equipment manufacturer. This next section covers confined spaces and other combustion air challenges. In addition to the NFPA recommendations that address getting additional air either from the outside or from areas inside the building, there are two other possible solutions to correct a combustion air problem. Additional air can be brought into the combustion air zone through the use of direct or indirect connections to the outside. A direct connection brings outside air directly to the burner. This can be done by an air boot that connects directly to the burner, such as the one showed here. There are different air boots for different burners, and it is critically important to use the correct one for the burner that it is installed on. The main factors that must be taken into consideration when utilizing air boots are that each model has a maximum equivalent length of the air intake run. Each elbow must be included in the calculation of equivalent length. Typical elbows have an equivalent length of 7 to 14 feet. The air intake must be supported and secured to prevent physical damage and joint separation. All joints and seams should be secured with screws and foil taped to prevent air leakage in the duct. A minimum of 12 feet of intake duct is recommended to temper the outside air being brought to the burner. A vacuum relief valve must be installed to guard against combustion problems associated with directly connecting burners to the outside, such as blockage of the intake termination, icing up of the ductwork, and the effects of wind. The vacuum relief valve will allow indoor air to be used if the outside air intake becomes blocked. If the heating appliance is sidewall vented, the intake hood must be on the same side of the building as the vent outlet. And because air inlet temperatures vary during the year, it's necessary to set the oxygen and/or carbon dioxide at different values for different inlet air temperatures. The burner manufacturer's guidelines for minimum and maximum oxygen and carbon dioxide must be followed. As this table shows, there is a significant difference in the recommended carbon dioxide and oxygen readings based on air inlet temperature. An indirect connection supplies air to the combustion zone by using a mechanical fan located near the appliance, such as the fan in a can pictured here. The fan must be electrically interlocked to the appliance with a proving circuit to provide air anytime the burner runs. A device such as a fan in a can operates as follows. Upon a call for heat, a relay is energized, which activates the fan. Once the fan is up to speed, an internal air pressure switch closes, completing a circuit and allowing the burner to fire. Once the call for heat has been satisfied, the fan and burner shut off, unless the fan has a post-purge cycle, in which case the burner shuts off and the fan continues to operate for a period of time. The main factors that must be taken into consideration when utilizing a fan in a can are: the fan unit should be located on a flat surface in the combustion air zone. Each model has a maximum equivalent length of the air intake run, and elbows must be included in the calculations. The air intake must be supported and secured to prevent physical damage and joint separation. All joints and seams should be secured with screws and foil taped to prevent air leakage into the duct. A minimum of 12 feet of intake duct is recommended to temper the outside air being brought in. A vacuum relief valve should be placed directly on the air inlet of the fan unit, and if the heating appliance is power vented, the intake hood should be at least 10 feet from the exhaust outlet and on the same wall of the building.